Now that we have enthalpy defined as really just talking about the heat that is gained or lost in a reaction, and we can ignore volume work changes, pressure volume work changes, if we're at constant pressure, we can actually kind of focus in on enthalpy for most of the way on out. We can just ignore the work portion of that. So we're going to get into a new part here, and we'll talk about enthalpies of reaction. So the energy that is gained or lost during a chemical reaction. And we simply just kind of refer to that as delta H is equal to the H of the products. So what did you end up with in comparison to the H, or the enthalpies of the reactants? That's where we're going to kind of focus on. Now, if we were in class and we were doing this on the board, this would be a time when I would give you like a worksheet handout kind of thing, and we would do lots of work looking at the enthalpies of reactants in products and the differences of those. But we're just going to do a little example right here, right now. We're going to look at methane gas. And we're going to look at the combustion of that, add some oxygen, spark it, and our products for any combustion reaction are always going to be carbon dioxide and water. And if I go ahead and balance this out, I won't spend any time going through that process. We'll get a couple coefficients in here for that. And I can tell you that the enthalpy change of this system is negative 180 kilojoules per mole of reaction, Rxn. And the one question I would ask you here is, okay, so if you have to put this value into this equation, where do you put it? Is it a reactant or is it a product? Energy is leaving the system. It's negative. This is exothermic. Maybe you've heard it before. Maybe it's the first time right now. Energy is exiting the system. It's exothermic. Therefore, it is a product. Now notice I'm adding a plus 890 kilojoules. This is a thermochemical equation with the energy listed into the equation. I think it's important to do this so you know if it's a reactant or a product, and you can kind of see it. You can treat it just as a thing. It can relate to any of these other variables in here doing stoichiometry. So we're actually going to do that. Here we go. I tell you that you have 4.5 grams of methane gas. And I ask you, how much heat does it produce? So given that, I don't know, we could write that in here and say, okay, I got 4.5 grams, and I need to get somewhere over to here. Just like we did with any stoichiometry problem, the only way you can get from one thing to anything else here is by having moles. Moles is your gateway to everything you want to get to. So let's do it. Start with what you got. 4.5 grams of methane times in a line. You had grams, so grams goes to the bottom. We have to be in moles to get into this equation every single time. All right, well, it's always going to be 1 mole. And the grams for this, 12 plus 4, 1 times 4, is 16 grams for every mole. And I don't need an answer for this because that's not what I'm interested in. But now, I'll put the methane thing up here. I need to get to energy, but I have, at the moment, moles of methane. I'm going to write moles of methane down here. And the energy involved in comparison, based on this equation, is 890 kilojoules of energy for every whatever number is sitting in front. If it was oxygen, it would be 2 down here. We have methane, which happens to be 1, right like that. And that's it. If I do the math here, I will end up with an answer of 250 kilojoules of energy. We're not done yet. Kilojoules of energy for this particular reaction. You need to signify if this is positive or negative one way or another. You could write down negative, and I'm just throwing it in there. I know some of you math people might be getting upset at the moment, but this is the energy that is released in this reaction. Released. The other thing you could put in here is actually writing the words. Released in the reaction, signifying that it is exothermic. Energy is a product. Okay? Let's kind of define some of these ideas or components in here, and then we'll do something in our homework problems. Calorimetry. Calorimetry is the measure of heat or heat flow. Now, just to kind of define a variable, typically when you measure calorimetry, you're not measuring the substance itself, you're measuring actually water. And just so something that we are aware of, it takes this much energy, 4.184 joules of energy per gram, to go up by 1 degree Celsius or Kelvin. Either one is fine. They work exactly the same. They are scaled the same. Okay. Now, two different ways we can measure this. One I just showed you. The other one I'm going to mention right now, called the molar heat. I'm going to spell my capacity with a K. Molar heat capacity. And the units for that one would be joules per mole per degree Celsius. I'll write it in this time, or Kelvin. Either one is fine. The other one we will mention is the specific heat or specific heat capacity, which is the one we just wrote down a moment ago, which is joules per gram per degree Celsius and or Kelvin. You could write either one. And this one sometimes gets the symbol of C, or sometimes C sub S, and that breaks down to Q over mass times change in temperature. That's where this would come from. And just to put labels on these so we can see it, Q represents heat, M represents mass, and delta T represents change in temp. Okay. And we could rearrange this equation right here to be something that maybe is familiar to you. Q is equal to CS times M times delta T. And you might call it something else like MCAT or something. I don't know. You have some name for it, which I'm not as familiar with. Okay. Let's set up a problem, and then we'll probably finish up in the next lecture. I believe we're looking at number 39. Grab some paper. Oh no, I don't need that yet. Throw this in here. 39. Here we go. For number 39, the combustion of ethanol, written there, to form water and carbon dioxide at constant pressure releases that much energy per mole of ethanol. Write a balanced thermochemical equation for this particular reaction. Okay, so it is the ethanol, and every time you have a combustion, you're going to have oxygen in there. So let's go ahead and write this out. And we'll write it the way they did, even though I don't typically like writing it this way. Ethanol, if it's being combusted with oxygen, and it is producing carbon dioxide and some water. Okay, and it tells us that it releases that much energy, and we will write that in right now. Kilojoules. Now we do have to balance this out. It's not balanced right at the moment. And I'm not going to spend any time going through all the parts here just to save a little bit of time. You can sit here and struggle on it right now. So pause if you like and take a look at that. Otherwise, these are the numbers that go in here. It's 1 ethanol, 3 oxygens, 2 carbon dioxides, and 3 waters. And again, this is the energy per mole of reaction. There it is. Okay, for part B, draw an enthalpy diagram for this. You may remember these from last year. You're going to have some initial set of conditions, and these are the reactants. I'll just write R. I don't know what the initial energy is. It doesn't matter. So we have energy over here, and we have some change in energy. Every reaction, no matter what, has to start going up. It's called activation energy. Wherever it starts, doesn't matter. We eventually get to something called the activated complex, which is up here, and then it's going to drop off. And for this particular reaction, it's losing energy. It's being released. It's exiting the system. Therefore, we're going to fall beneath the original and release a total amount of energy of 1,235 kilojoules. So it goes down from this point by that much energy. And again, this is an exothermic reaction. Okay, that's good. This should be the end of this particular lecture.